Good morning, everybody. My name is Emil Lezak, and I have the pleasure to start final conference of InnoWEE project. The full title of the project is Innovative Prefabricated Components, including different waste construction materials, reducing building energy and minimizing environmental impact. On the final conference, we have 14 speakers from the consortium team and also invited speaker. On the audience, we have different representatives from the sector related with the building and construction from different countries like Spain, Norway, Italy, Hungary, as well as United States, Thailand. So now the first presentation is of Adriana Bernardi, our coordinator from CNR ISAC, who give the welcome to the participant. So Adriana, the floor is yours.
Thank you very much, Emil. Good morning to everybody. Thank you to be here to assist to the presentation of all our good results of this project that is a project that, in my opinion, but I hope that you share with me this opinion, is gives a very good result that we are presenting. So this I will give you an overview of this project. And after my presentation, you will assist to go deeper in the detailed things that I give the first images. So we go to the project. The project was a 4-year Horizon 2020 project, a research project financed by the European Commission. So it's a project that go until a pre-industrialization level, not something that is already in the market, but is ready to reach a good level very shortly to go to the industrialization aspect. So we know that we have a lot of waste. For example, you can see here written how much waste we produce in 2010, 2 billion tons, and these tons need to be reused in some way to have a green economy. So we have a lot of ton of waste to reuse. And we try to reuse this waste to produce prefabricate panels and to try to use to have this panel to arrive also to energy save in the total balance. So I present you the consortium of InnoWEE. Is 10 partners. You can see the distribution in Europe of these partners. We are very sharing all Europe, so good dissemination of the results, and some of this partner you will have the presentation of the next lectures. So we have the objective. I just show you the objective of InnoWEE. We recover, disassemble, and select this waste to produce high quality of raw materials to be used to produce the panels. Finally, we produce this panel, this construction product to be used in the construction field. And after this production, we demonstrate in real field in different scenario and the different kind of panels. Finally, we go to demonstrate that they are cost efficient, and we will build the business model for the future application in industrialization field. Finally, we as usual, we produce guideline, training material, and we do a big dissemination, notwithstanding the problem with the COVID that limited some, at least in presence. What were the phases of the project? The project was divided in these 5 phases. The first was selection of this waste and to put in the panel to reuse. The second phase was the realization of the panel and to arrive until the scale up of these products, to be ready to go to the third phase, that is the demonstration in real and virtual case studies. Finally, we have a fourth phase, the consideration how is the economic process to go toward the market, and of course during all the project we had the dissemination, exploitation, and all to share during the evolution of the project all the results. The innovations that we produce was they treat the waste, the CD, to yield the suitable raw materials and use a new environmental friendly binder that are the geopolymers. And here is the novelty that we use friendly and green product instead of concrete. You can see here very shortly, you will see more detailed after my presentation, the production of InnoWEE secondary raw material. So we arrive from the selection to reduction size to arrive at a final dimension very fine, from 0 to 2 millimeters that will be included in the geopolymers that are in producing high density geopolymer panels with a 50% of inorganic CDV and wood geopolymer panel with a 50% of wood of CDV. This is a short figure that show the 4 kind of panels that we will produce and will be detailed in the next presentation and explain how we arrive to these panels. We produce this panel were tested with different methods in lab. We installed the prototype at a test wall before to go toward the field, and we scale up the panel to produce enough quantity to be installed in the real case study, and finally, of course, distributed in the demo site where installed. What are the demo sites? We had 4 real demo sites. We had in Padova, in Italy. There were a pilot house where we do all the tests before to go toward the field to install in the real houses or building, different kind of building. And after this first test, we go toward the real demo site. There is one in Greece, in Athens, in Bula in particular, a nice village near Athens, and in a historical classified building. So we also involved building that were historical building to see how we could use these panels also in more complicated situation like the historical building. We have another one that is input Mechelen in Belgium, and this is a eco house, is a residential house built with eco materials, particular also in this sense. And after we have Don Orione Care Center in Bucharest, in Romania. We have also in this real demo site we install, as you can see shortly in this image, the different kind of panel. And finally, we had also a work that was interested in terms of virtual demo site. This means that they are real demo sites, but not the application of the panel was not real, but was virtually put on the walls and see the effect and modelize the effect of this use of the panel in this demo site. As you can see, one is in Italy, one in Greece, one in Romania, and also in Bilbao. So we did, as I said, this simulation. This is just a little image, but there is a colleague that will present all the results and the modeling of energy performance of this product to find the best solution in terms of efficiency and comfort. As I said, these are the other aims of the project. So I thank you very much. I give the floor to my colleague that will be more complete in the explication of our results. And
thank you, Adriana, indeed, for this presentation of the project. So now the presentation will give Daniel Lisic from HUP, Slovenia, on the challenges and opportunities of construction sector in terms of secondary raw materials implementation. Daniel, the floor is yours.
Thank you, Emil, for that. Good morning to everybody. I wish to thank you for the invitation to have this opening presentation. I am Daniel Lisic, member of advisory board, and we have presentation about SRMs from, let's say, industry point of view. First, just quickly to introduce the working background. I work in R&D for a company EU from Slovenia, which produces materials for finishing works in constructions like paints, facades, mortars, and plasters, EPS insulation, and so on. EUP has around 100 million euro turnover and is present on over 20 markets. Sorry. So in my presentation, I focused, besides some slides about global trends, mainly on our experiences during our steps in implementation of SRM in our production and challenges we were facing doing that. I think that is always interesting to see others' experiences and challenges we had can basically be generalized. Of course, challenges are at the same time also opportunities, but at the end I will talk separately also about opportunities that are connected to European policy. But first, some words about global trends. The circular economy is now a global trend, and Europe is, at least to some degree, a leading player. One of the main European strategic goals, beside environmental, is to become less dependent on global raw material supply, to be as much as possible self-sufficient. And as we can see in recent years, and what COVID crisis showed even more, is that we can expect in the future that global supply chains will get somehow shorter, and own source of raw material will mean advantage on the global market even more than it is now. On this slide, you can see the price and trade volume of some wastes through years within Europe. Price of the waste plastic and paper drops in recent years, while the price of the waste glass isn't. The price of plastic waste depends on the crude oil price, which is connected to price of virgin raw material. On the other hand, it depends also on supply and demand. As can be seen on graph, price drop in Europe was influenced also with plastic waste import ban of China in 2017. Such a big stakeholder can have a big impact on SRM market. The same goes for waste paper for recycling. On the other hand, question arises why transport ceramics on such distances and not to find ways to effectively use this by ourselves. So let's see some challenges for SRM implementation. One of the challenges is to have a consistent quality of SRM. The reasons for quality variations can be different, like different source through time or source mixing, impurities. When we developed isolated concrete forms from EPS for nearly zero energy housing, the plastic brackets between EPS walls are made from polypropylene, and when we tested tensile strength of brackets from virgin raw material, the results range was quite smaller to the recycled one. Although the average tensile strength was even a bit higher, we choose to produce brackets from virgin polypropylene. During pouring of concrete on construction site, we cannot afford that some brackets broke because we could endanger work's life. So it's also intended use that could make importance. And such a broad result range was not acceptable for us. Decision on use of recycled material for buckets was easier. The main problem could be in the shaker, the tinting machine, but there is no danger for workers' lives if failure occurs, so only the machine life. So, but we have quite challenges during introducing of plastic handle instead of metal one, because handle must be more elastic while bucket not, but they are made in some extrusion process. When you come to price competition, we have two situations. So the price of the SRM could be higher than virgin raw material due to demanding technological processes for collecting, sorting, cleaning, and transporting. Another thing is that final product could be expensive if we want to have the same end properties. This was the case with brackets in isolated concrete forms. Another thing we could do is to prescribe smaller concrete pouring height, but this would also be a disadvantage. Another challenge is to dismantling and separating materials. This could be a problem when having composite products, such as, for instance, ETICS facade. On the picture on the left, you can see different layers that are adhered to each other, and thermal insulation is glued to the wall. Ventilated facade, upper right picture, have advantage in this manner because everything is screwed and usually not glued. But also ETICS system solutions are seeking. You can see a solution from company Stowe where insulation is mechanical fixed to the wall by anchors. Then special anchors in combination with boards with hook and the loop surface was developed. You can see on this slide. And at the end, you get the classical look when you apply mortar. It is always desired that separation can be done on the site, so material for recycling can be transported directly to processing without intermediate stop at collectors, which demand then labor work and additional transport. Also, small steps are beneficial if you take in consideration that millions of buckets are sold every year. So besides changing to recycled plastic for smaller buckets, we introduced plastic handle, as I told you before. As you can see on the picture, on the bigger bucket handle is from metal and have also small plastic holders, so it's much more complicated to separate it. Here I present one interesting way from Sony company how to treat EPS package waste. It is not something new, but I like the idea. They extract oil from the peels of grapes, which dissolves EPS. The truck with the limonene oil liquid have tank in the back, and it goes around and collect EPS waste from the stores, with which they reduce transport costs of lightweight big volume material. One vehicle can collect the same amount as 10 trucks. After collection, limonene and polystyrene are separated and can be used again. Another thing is public perception and health. The perception about recycled product in public could be also negative. For instance, about 2 years ago, one of our salesmen from Italy asked me for declaration that one of our products don't have any recycled raw material. At first, I thought that I understood him wrongly, but on the end, we saw that investors specifically wanted product without SRM. So choices of millions of consumers are important and can support our abstract circular economy. So right and credible information must be provided and communicated. A lot of so-called green science and green statements can be found today on markets, and consumers often don't know how to compare products or which information to trust. Another, I think, big challenge is impact of reaching regulation on SRM market. Constantly new chemicals causes concerns about health and environment. For instance, EPS for facades contained till 2015 flame retardant, which is now on the list of dangerous substances. In the future, there will be problems with such waste. So European EPS industry started the project Polystyrene Loop to overcome this and to find the solution which will be also economically feasible. It is one of good examples. It takes a large investments and cooperation of all major players. And when talking to health, maybe also one our experience, we thought to cooperate with some partner who offered us clay at a very good price and enough quantities. But when we tested it, we found that crystalline form can cause asbestosis-like illness. Of course, we didn't use it, like I think nobody would, but it's always danger that someone, let's say, unintentionally due to less thorough testing, would use it. Such things could then shed bad light on SRMs and bad image in public. At the moment, SRM share of raw materials in European Union is generally still small. We all know that EU starts circular economy package, and we can expect a lot of investments in this action plan. But my intention is not to talk about the circular package details. I want to point out that we are in a similar phase like we were some 20 years ago with energy efficiency. At that point in time, beside experts, only few enthusiasts know what is heat pump or passive house. Today, after a lot of investments, new business opportunities, new business models, jobs created, heat pump is standard solution, everybody knows, and nearly zero energy building is now in EU regulation. I believe that in 2040 this will be the case also with circularity, and eco-design will go hand in hand with energy efficiency. And for companies, it is important to be part of this transition in early stages, because afterwards it's always tough to catch the competitors. One of the tools that member states have to promote implementation and are already in use with more or less success are green public procurement and green taxes. The price is always the key factor which influence the decision about order, and with green taxes we can ensure that environmental costs are better included in product price. Waste management is crucial part of circular economy, and here is, I think, opportunity for producer to become also to some degree a suppliers, or at least establish partnerships with waste suppliers. This, I think, is important because waste collectors or suppliers are usually fragmented, and bigger manufacturers with their specific needs can connect them on a broader level, maybe also in the shape of some public-private partnerships. Here I prepared a pyramid-like scheme, how companies could be involved in circular economy. I will give an example how Europe as a EPS producer could participate in closing the EPS loop. The use of recycled plastic for buckets, as shown before, is right blue angle of pyramid. We get some partner of SRM source and use it in extruder. Simple industry. In industry we love such solutions. But if we want to somehow recycle polystyrene, we could go on the left side of the pyramid, but in that case only for EPS without dangerous flame retardant. We could establish partnership with waste collectors. They must know how to separate EPS from dangerous one. Invest in the equipment for compacting EPS. And if we want to use polystyrene forward, we should invest in plant for extrusion of polystyrene. So a much bigger effort than in previous case. But recycling EPS with dangerous flame retardant is something that is beyond companies like UP. This is a red top triangle, but we could be some small part of bigger supply chain, invest in local collecting and processing plant and deliver polystyrene resin to, let's say, BASF, which will use it to produce EPS beads, which we will finally use it again for expansion of polystyrene. And for conclusion, I think global trends towards reuse is irreversible. EU strategy, we are at a similar point like with energy efficiency some 20 years ago. Energy efficiency made technological progress mostly just in housing part of construction sector, while circular technological process will include all construction industry. So we come to the end. I wish to thank you again for opportunity to be part of final conference of such interesting project. And I really look forward to hear next presentations about final results of the project, and really hope that this is just the beginning of a successful story. Thank you.
Thank you, Daniel, for interesting content. Indeed, the green transition, which followed the circular economy principles, is the key aspect in the relevant roadmaps and directives of the European Commission. So this was nice to see. Now I give the floor to Sergio Tamburini and Giovanni Ferrarini from CNR, ICMATE and ITC respectively. The presentation will be about innovative geopolymer panels from waste to laboratory realization. So Sergio, floor is yours.
Okay. Good morning to everybody. I'm Sergio Tamburini from CNR ICMATE, and I talk about what already said, innovative geopolymer panels from waste to laboratory realization. Okay, construction and demolition waste typically comprises inert inorganic mineral materials like concrete, bricks, tiles, and so on, with smaller amount of other components. But it's important to say that construction and demolition waste accounts for approximately 25–35% among all waste generated in the European Union, and in 28 countries of Europe, the CDW stream is about 0.81 billion tons per year. So the philosophy behind the waste problem can be schematized in this inverted pyramid, in which the first objective is produce less waste. Then reuse as much as possible of what is disposing, for example, or using roof tiles that are still good. Then recycling the waste in another form. Then recover also by transforming, for example, producing energy. And at the end, as a last resort, landfill on disposal. When working with waste materials and their recycling into new products, different legislative documents need to be considered. Documents related to waste and legislation related to new building products. In our project, the classification waste was made according to the list of waste, and these were the waste we have used in our project. To improve the collection of materials for reuse and recycling, selective demolition and also appropriate on-site operation are required. For this reason, the waste management protocol was made in 2016 from the European Union and defined these 4 points. First, pre-demolition audits and identify the construction demolition waste generated, what kind of materials. Then produce a waste management plant, define the different steps of demolition and how and by who will be performed. Then perform a selective demolition, separation of all materials, hazardous waste separated from the other, the construction, separation and fixation of the materials, and at the end, the fourth is processing and treatment. And after this process, the material can be prepared for reuse or recycled or disposed of if there are no other choices. In the InnoWEE project, after the demolition process, the last step of processing and treatment of construction demolition waste was performed by our project partner ECO from Italy, that has transformed the CDW in secondary raw material. For the production of this secondary raw material, they have used the 30-60 mm fraction of their procession plant. This was the procession plant. Further refinement by an additional screen was necessary to meet the desired dimensional range for the project 0 to 2 millimeters. The transformation into secondary raw material permitted by local authorities has been updated with construction works to comply with environmental prescription as dust reduction or sound absorbent barrier and so on. To comply with end of waste criteria specific set by local authorities, the obtained secondary raw material are analyzed in laboratory to verify that they meet the prescribed physical and chemical requirements, and so were performed specific procedure described in the standards. For example, macroscopic composition on organic waste, mineralogical, chemical, qualitative phase analysis, particle size distribution, density, water absorption, leaching test. Leaching test was quite important because it's important to identify the heavy metals present in the waste, then geopolymeric reactivity and other analysis. We said that one innovation introduced in the InnoWEE project is the use of geopolymers as a new ecological binder. Geopolymer are inorganic materials produced in a process in which aluminum silicate are activated with alkaline solution. The name geopolymer means that they mimic natural compounds such as zeolites and exhibit the main properties of rocks: hardness, chemical stability, and geological longevity. The name contains the word polymers because they are obtained by a polymerization process called polycondensation. It's important to say that 1 ton of geopolymer produces 0.16 ton of carbon dioxide, while 1 ton of Portland produces 0.87 ton of carbon dioxide. It means that geopolymer is an environmentally friendly material. The reagents to produce the geopolymers are aluminosilicate and alkaline solution of potassium or sodium. Aluminosilicate used also in our project can be clays like kaolin, calcined as metakaolin, or slag wastes that come from the iron production process, or fly ashes, other wastes from energy production plants. Other aluminosilicate are pozzoline, very common. To these reagents we add inert materials, in our case construction demolition waste, and variation produce a liquid that is poured in a mold to produce the geopolymer material. Geopolymer do not require the presence of Portland cement to harden, as we have seen, and show the best properties of ceramics, cement-based materials, as they have a good material mechanical performance, excellent adherence to aggregate, are a fire resistance, has a good resistance to acids and chemicals, and has a low hardening temperature. Using the geopolymer binder produced mixing metakaolin, slag, fly ash, silicate, and so on, we obtained two kinds of products by inserting inorganic construction waste or construction demolition waste, or wood waste. That is another is a construction waste. The first product, called high density geopolymer, contains 50% of inorganic aggregates, and the second contains 40–50% of wood from construction waste. The research carried out to optimize this binder was very important, was the core of this project. It was also very difficult because you had to take into account several aspects. First aspect was the creation of panels, and therefore the possibility of creating large panels with good mechanical properties and no defects, possibly. And the second aspect is the production process of a panel. That requires certain characteristics of a mixture, such as fluidity, workability, long setting time, and so on. Another important aspect was the cost of the materials and the final panel, and the life cycle assessment of the process. The innovative, efficient building panels produced coming from this geopolymer mixture must have important technical characteristics. We had to comply first with energy efficiency, and therefore must have comparable performance with the products on the market. They also had to comply with national and European construction standards and regulation. They had to comply with industrial processes, and therefore, as I said before, low viscosity and so on. They must have also compliance on the design of these panels, because these panels have to be compatible with known installation technique and with the materials used by workers in the sector. Lastly, it also had to comply with safety requirements, and therefore the panels were designed to withstand the wind loads and the seismic activities, and this has required accurate simulation and effective anchoring system. How to find the best recipe to produce the right panel? It starts from a basic recipe, and then with a try and error process, changes are made on the components and granulometry of all these parameters. After the properties of the individual recipes are tested with mechanical, chemical, physical characterization. If there are problems, you go back to change the initial recipe. If good results are obtained, we move on the production of large prototypes where the defects that the initial mixture can produce are highlighted. In the case of important factors, you come back to change something if the process go on until the final product is satisfactory. About characterization, the first characterization serve to qualify are certainly mechanical characterization performed on all sample produced, compression test, splitting that evaluate the tensile stress and bending stress, and then other parameters were investigated. These are some examples. For example, the suitability of a waste, the content of a waste used, bricks or cement, the particle size distribution. Then talking about the reaction, the rate, about the reagents, the use or not of short or what kind of short fibers. Then the process, curie temperature, fluidity, open time, and so on. The final recipe that has been obtained to the best of the parameters we have described is a compound that has a compression strength of about 40 megapascal at 28 days and viscosity about 120 pascals per second, and open time after 100 minutes with a viscosity of about 600 pascals per second. Starting from this recipe, a patent application was filed. The aim was to protect this invention, and together with the recipe, also we have protected also one of most performing products obtained, the radiant sealing panel, which has shown particular efficiency properties, and we talk about this in the next slide. These are the four kind of panels produced of three types. The first is an ETICS panel. ETICS means external thermal insulation composite system for external use, mainly in commercial buildings. The second is a ventilated facade panel, always for external use, mainly in commercial building. The third is a radiant panel for ceiling or wall, both for residential and commercial buildings. Talking about how these panels are constructed, the ETICS measure about 50 per 50 centimeters in prototype. In the prototype type, but when in production was 40 for 19 centimeters, and as an external layer of about 8 millimeters of high density geopolymer and internal APS insulation with a weight of about 18 kilogram per square meter. Is mounted in special anchors, and the design is a particular with shifted EPS edge that allows the overlapping of the panels to reduce the thermal bridge. It was used also for an easy dismantling at the end of the life of the product. Talking about a ventilated facade, the dimension is 60 by 60 and the weight of 25 kilograms per square meter. Is built as before 8 millimeter of high density geopolymer plate, reinforced with geopolymer rings of 3 centimeters and metal fibers. In the back, we have used a particular kind of geopolymer made with wood to improve the impact resistance. It can be mounted on a metal structure and with a special anchors system. The last panel is an Hydronic radiant ceiling panel with a side of 60 centimeters, weight 21 kilograms per square meter, and contain an internal hydronic circuit, and the external surface is always the same high density geopolymer, and with 55 centimeter APS insulator in the back. Has a very good thermal performance and is mounted in false ceiling, and the connection are on the back side. How to produce this how is the process to produce these panels. The manufacturing process is similar for all the 3 types of panels. For example, for ETICS 50 by 50, the panel was produced with a geopolymer casting in a casting box, then where you can put also a texture that gives an aesthetic finish to the panel. Then the box is vibrated because the geopolymer has thixotropic properties and that helps to spread the material. Then we put a fiberglass net, then the EPS layer, again pressure and vibration, then everything is closed with the lid, and after vibration the panel is placed in a sealed bag in an oven for curing for 12 hours. Then after 5 days of curing, the panel is ready to be worked to finished with painting, for example. In case of ventilated facade geopolymer casting, there is a similar process, but using a more complex mold. As we said before, the panels have been designed to be safe. A series of tests of pull-off were carried to evaluate the bond strength between geopolymer plate and APS in the back. Other studies, for example, were on impact resistant to be able to use these panels safely in open space, and then the design of these panels and the anchoring system, as we said before, was assisted by 3D finite elements modeling to ensure compliance with Eurocode and anti-seismic wind load guidelines. Particular attention was given also to the finishing of the surfaces and also to the surface texture, thanks to Geopolymers' ability to copy microscopic details. It is easy to give the surface a particular design. The natural color of the geopolymer in our case are determined by the type of waste inserted. Gray if concrete, red if brick are predominant. In our case, thanks to the other partner AMS, multifunctional color paints have been used that contain additives of a nanotechnology field that were used to enhance properties such as reduced water absorption, cell cleaning, antibacterial, anti-mold, and thermal reflectivity. To conclude, at the beginning, we show here how the project was concluded at the prototype level. We are producing in 2018 the ETICS ventilated facade panel that were installed in the Padua near the CNR facilities. After this, the process of upscaling started. Thanks for the attention. Now I give the floor to my colleague Giovanni Ferrarini, who will talk about the thermal properties of his panel.
Yes, thank you, Sergio, for interesting presentation with plenty of technical details about geopolymers developments. So, Sergio, Giovanni, the floor is yours. Please follow with your content.
Thank you, Sergio. Thank you, Emil. Good morning to everyone. I'm Giovanni Ferrarini from the Construction Technologies Institute of the National Research Council, and I work in this project with my colleagues on the thermal optimization and measurement of the geopolymeric material. Firstly, we started with the study of the mixture, and the main parameter is the thermal conductivity. So higher values are beneficial for radiant panels, while lower values will be beneficial for ETICS insulation. Another parameter is heat capacity. Heat capacity is the product of the specific heat and the density. For the heat capacity, higher values will be beneficial for the thermal inertia of the ETICS panels. On the right of the slide, you see the three instruments used to measure respectively the thermal conductivity, the specific heat, and the density. And we have two ways to obtain different values of thermal properties. The first option is changing the amount of construction and demolition waste that are inside the geopolymeric material. And the second option is working on the porosity of the material. We have measured a wide range of mixture, and on the image on the top right, you can see some examples. We have found that the high density geopolymer can reach very high thermal conductivities. We are in a range of almost 0.91 watt per meter Kelvin. That is 3 or 4 times higher than the standard value of the plasterboard that is commonly used for radiant heating. Also, wood geopolymer could reach quite good thermal conductivity values. And the thermal capacity, said the product of specific heat and density, can be very high for the high density geopolymer. And as said, this could be beneficial for the thermal inertia of ETICS panels. We tested also the thermal behavior of ETICS panels in two ways, steady state and transient state. In steady state, we measure the thermal conductivity with the standard method, EN ISO 8302, using the hot plate apparatus. We tested both the laboratory production from ICMATE and the upscale production from AMS. For the transient state, instead, we proposed a novel test. As the finishing layer has a role in the dynamic thermal conditions that are typical of the summer season, we wanted to investigate this behavior. So on the right, you can see, on the bottom right, you can see a thermographic setup for the measurement, where we use lamps to simulate the thermal stimulus of the sun, and we record the surface temperature of the panel during a test. The results that we obtained are good both for the steady state, as the values are compatible with the measurement on the laboratory samples that I showed before, and are good also for the transient state, as the calculated value is very, very close to the measured one. Now I move to the radiant panels. Here we made some optimization of the design of the radiant panels before the production. We made a lot of numerical simulations in 2D to investigate different geometries of the system, to quantify the impact of the thickness of the finishing layer, and of the thermal conductivity of the geopolymer, and a lot of other parameters. And this 2D simulation contributed to the final design of the panel. While on the final configuration, a 3D model was implemented, and as you can see from the two images on the bottom, and the left on the right, the agreement between the simulated values we obtain on the numerical simulation and the measured one is remarkable. Finally, we tested the upscale production of radiant panels. We have a dedicated facility at the CNR laboratories in Padova to test radiant panels. You can see in the top image of the test room that is designed according to the standard, and on the bottom, the installation of the ceiling panels under test. Also here, we have performed both steady state and transient measurement. The steady state thermal output, as described by the standard, is the main characteristic, but it is interesting also the transient measurement, because we are able to determine the time constant to understand how fast are the panels to provide the thermal output. Here we have some results for the steady state, and the panels were tested both in heating and cooling mode. These are the red and blue curves at different temperatures of the water inlet. And the thermal image on the left shows the surface temperature of the panel during a test. And these panels are very homogeneous, and as expected from the numerical simulation, the thermal output is higher than a traditional commercial solution with plasterboard finishing. In transient mode, we display the surface temperature after turning on the system, and you can see images at 5, 10, 30, 60 minutes after the start, and the curve of the average surface temperature shows that these systems are fast with a time constant that is around 15 minutes. So thank you very much for your attention, and I give the floor to the next presentation.
Thank you, Giovanni, for your part of the presentation. Indeed, it was interesting as well. And well, now is the turn of Maria Papa from AMS Greece, which give the presentation about pilot plant and upscale production of the new panels. Maria, floor is yours, please.
Hello, everyone. My name is Maria Papa, and I will speak about the pilot plant design, the construction and the operation for the production of the new panels that took place in AM Solutions. Unfortunately, my colleague Konstantinos could not be present today due to some health issues, so I will be the only speaker on behalf of AMS. I don't know, Emil, if you are able to see my screen?
Yes, it is correct. Please follow. Okay.
So I'm a chemical engineer, and I work as an EU project manager with expertise in energy efficient buildings projects in AM Solutions. For some reason, I cannot change my slide. Okay. I guess you can see my next slide now.
Yes, yes, correct.
Okay. So the new panels that were presented before by Giovanni and by Sergio from CNR had to be tested in 4 physical demo sites, as also was mentioned by Adriana. And as you can imagine, such a demonstration demanded an upscale production, and this was the main activity of AM Solutions in the framework of the EU-funded project InnoWEE. And more specifically, I will present the design, the construction of the pilot plant, and finally the production of eco-friendly insulating facade panels and radiating panels for wall and ceiling, and also some assessment of the pilot plant production. So, trying to upscale the high-density geopolymeric panels was not an easy task. It was clear from the beginning that modern methodologies and modern technologies had to be adapted in order to reach the desired result. So AMS decided to apply for the panels production the Six Sigma methodology, which was firstly developed by Motorola in 1980 and is known as DMIC, which means, as you can see, define, measure, analyze, improve, and control. And this is a case-driven procedure that is used for improving, optimizing, and upscaling processes, and finally produce zero-defect products. This is the final target. When we say define, we mean identification of all products and production requirements, which these will set up the design requirements and the framework. And the next step is measure. Once the first step will be completed, then in the pilot plant will be produced a range of samples and will be tested for their properties. And this is a trial and error period that is necessary to determine the best possible setup of a production line. The third is analyze. And all results from trial and error period will be collected and analyzed according to the means of repeatability, quality, and a database of statistical data will be developed. The second phase is improve, and here implement modifications from analyze phase and start the training of personnel, and finally control, which means that we will have to set up benchmarks, ensure process repeatability, apply quality control process. Well, at the beginning, we identified from lab scale production that took place in CNR, the materials needed for the production of the high density geopolymer panels, paste, a lab scale production methodology, the approximate processes duration in lab scale, some of the process specific requirements, the required equipment, etc. Though it was clear also at the beginning that there were still a lot of issues that needed to be clarified, such as the auxiliary processes and utilities, critical tasks, production tasks, influencers, which means which tasks were influencing other production tasks and how they were influencing them, relationships among processes, the personnel involvement, etc. So it was decided to go back in the Six Sigma methodology and search solutions to its inventory of tools and adapt the 4D or otherwise double diamond holistic approach, and split the overall process in the 6 stages that you can see in the scheme, in this scheme at the bottom of the slide. The 6 stages are the preliminary design, where all issues related to the design are identified. Then is the detailed design, modifications in the pilot plant, all modifications of the detailed design applied in the pilot plant, the trial and error period, corrective actions, and finally the actual production of the high density geopolymeric panels. Here is presented the basic flow sheet that gathers all details and results from the lab scale production and implements them in blocks and boxes, indicating their relationships and the production flow. Briefly, the basic flow sheet helps the designers to identify the required production and their duration, the equipment that will be used, the utilities that are needed, any auxiliary processes, the role of personnel, the quality assurance policy, etc. From the basic flow sheet, we were able to identify the critical paths of the overall process and develop a PERT diagram, set up a working stations diagram where each employee knew exactly what needs to be done and how, and analyze the production processes relationships. And the outcome was, as you can see in the bottom right, to establish the production-like conditions and also be aware of the limitations, adapt pilot plant conditions and know the limitations, and also identify failures and risks. And this is the pilot plant for the production of the new panels. Regarding the concept and the principles, as you can see, the modular operation was decided to be adopted. The pilot plant capacity was up to 700 kilograms per batch and can be easily updated to 2,800 kilograms per shift, can operate on a continuous basis if this is needed, and 80 to 85% of the processes were automatic or semi-automatic. And here is the technology upscaling pilot plant that was used for the production of the InnoWEE panels. AMS's pilot plant is located in Acharnes, in AMS facilities, and the pilot plant existed before InnoWEE and was equipped with all required infrastructure like the electrical beam, water and ionized water supply, etc. Auxiliary systems, power backup systems such as UPS and generators. A fully equipped laboratory for a wide range of testing existed, and a wide range of machinery and equipment such as mixers, conveyors, tanks, motors, the painting room, etc. And here is the technology upscaling pilot plant that comprises of 6 modules. The first module is the storage of the solids and the premixing. The second module is the storage of liquids and the feeding to the main mixer. The third is the main mixing and the feeding to filling station. The fourth is the casting. The fifth is the curing and the post-curing storage. And finally, the 6th module is where the preparation of EPS took place, where we paint the panels, we package them, and we storage them. Here you can see some of the modifications that had to take place in the already existed pilot plant in AM Solutions. Almost 200 modifications took place in order the pilot plant to be able to be used for the production of the panels. You can see modifications in the premixing buffer, in the PLC programming, also in the mixer scale, premixing buffer scale, in the main mixture, etc. And here are the production line simulations and modeling that had to take place in many points and many phases in the production line, like for instance, in the liquids feeding line, in the cold and hot water supply, in the mixing, in the nitrogen supply, etc. This is how the production line in AM Solutions looked like in May 2017, just before the modifications started. And here is the situation after a year in May 2018, when we finished with all the modifications and we were ready to produce the InnoWEE panels. And here is some statistical data. As you can see, for the radiant panels, the production lasted 20 days and 55 items were produced, and the geopolymeric paste was around 400 kilograms for the radiant panels. For the ETICS, the production lasted 77 days, 264 items were produced and almost 2 tons of geopolymeric paste. And finally, for the ventilated facade panels, the production lasted 42 days, 85 items produced, almost 700 kilograms of paste. And regarding the Six Sigma ranking and the defective panels, you can see here that we had 2.1% defective ETICS panels, 0.63% defective ventilated, and 0.33 defective radiant panels. And regarding the Six Sigma ranking, it was 3.06%, so between the levels 3 and 4, and this was a very, very good achievement, as the usual ranking for a pilot plant production is much lower, is between 2 and 3. This was from my side. Thank you very much for your attention.
Thank you, Maria, for presentation. The public has the possibility to see the substantial things related with the production. The video is available on the InnoWEE website, innowee.eu. So thank you again. Now is the turn of Mrs. Wilma Dukman from ZAK Slovenia to give the presentation on testing of the new products. Wilma, turn is yours.
Okay, good morning to everyone once again. So my name is Wilma Dukman and I'm from Slovenian National Building and Civil Engineering Institute. Today I would like to present how we have performed testing of these new developed products within the InnoWEE project and how we evaluate them for the intended use. Now, do you see?
Yes, in edition mode.
Yeah, I can try this way.
Yes, please follow like that.
Yeah, I will do this way. So, as I have said, I will present what has been tested in these new products. I would like to stress that for every product on the market, it's important that somehow proves that it fits for intended use. And for building sector, this is even more strict since testing and CE marking is obligatory according to the construction and product regulation. So for the most traditional building products, harmonized standard exists, and this standard prescribes what and how the product should be tested. But for new innovative products, these are usually not covered by harmonized standards, so it might be a problem or an obstacle how to come with such product on the market. If we refresh it within this project InnoWEE, we have developed 3 types of building products. First one is ETICS-like panels, second one is ventilated facade panels, and the third one is radiating panels. And for all of these products, there is no standard available for this material. So how we tackle this problem? In order to adequately test them, we have studied standards for cement-based products with the same intended use. And we have decided what we need to test and which condition of exposure will be, which condition will be exposed. So, like, for example, freezing. Then we have checked which parameters are important for this intended use, like, for example, mechanical properties, water absorption. And finally, we have also checked state-of-the-art literature and knowledge regarding potentially problematic parameters, because this product differs in chemistry of cement-like products. It's geopolymer products, as was explained before, so the chemistry is not the same as for the cement-based. So we have finally decided, based on the search of different standards and guidance, that we will use the test procedure described in 2 ETICS. One is ETICS 004 for external thermal insulation composite system with renderings, which is the closest to the ETICS-like panels. Second one is ETICS 043, which later on was superseded with another European assessment document. And for the durability aspect, we have selected that we will follow state-of-the-art procedure adopted within the different trialing committees. So with this durability testing methods, we cover alkali reactivity, sulfate resistance, carbonation resistance, but also freezing in the presence of salt. So at the end, this is the list of the standards test methods which we have performed first on the laboratory produced prototypes, and later on also on the pilot samples from the pilot production. So I will present now first results from the laboratory production and compare them later on with the results from the pilot production. So the list of the selected tests is determination of porosity, capillary water uptake, water vapor permeability, resistance to freezing thawing, also in the presence of de-icing salt, resistance to carbonation, alkali-silica reactivity, sulfate resistance, and also bond strength and impact resistance. So the first one, it's more like identification test. It's not required in any of these standards, but this is fast test method, which gives information about density, porosity, and pore size distribution. And as such, it can serve as identification test to compare different samples with each other. So here you can see the results for two types of panels, for the ETICS-Iike panel and ventilated facade panels. What we can see is that the results are pretty similar. The composition is the same for both types of panels. The technology production you have seen just before, it's similar. So we expected also that these values will be pretty similar for both of the panels. So the next parameter, which is important in the for the facade use, is water absorption test. Water absorption test also covers the same parameter as previous test. This is porosity. And in this way, it's determined through water absorption after 1 hour and after 24 hours. Here it's written in ETICS 005 that if the water capillary absorption is above 1 kilo per square meter after 24 hours, then the material needs to be tested for freezing test if it's resistant to the freezing. In both cases of our ETICS-Iike and ventilated facades, these values was over what is prescribed for cement-like materials. So we decided that we will perform freezing test. Freeze test, we expose samples to 30 cycluses from -20 degrees C to 23 degrees C. And as you can see also from the figures, we have confirmed that after 30 cycluses of freezing thawing, there is no cracks or any damage on the surface of the samples. So no cracks were identified. We can say that samples are freeze-thaw resistant. But the standard requires that after freezing, it's important that adhesion of geopolymer layers, or in ETICS 00 point, this is cement layer, to the insulation layer is still high enough. And we have tested this parameter before and after freezing with pull-off test. What you can see here is value before the freezing thawing and after that, after freezing thawing. You can see that the adhesion is a bit lower, but still sufficient enough, because it should be for the cement-based material, it should be at least 0.08 megapascal, but in our case, it was 0.11. So it still fits for the intended use. For the ETICS-Iike panels, it's also important that water vapor diffusivity lies in certain range, because otherwise there is a risk of condensation between layers. In ETICS 004, the water vapor diffusion equivalent, so-called S value, should be below 2 meters. And in our case, for both panels, it's important only for ETICS-Iike panels, because ventilated facade is not so important, but we tested them parallelly. It's 0.6. So again, we can see that it fits for the intended use in regard of water vapor permeability. The next parameter, which is important when such panels are used in the lower part of facades, it's important that withstands impacts from different objects like stones, balls, bicycle, and so on. In order to improve impact resistance, usually mesh is incorporated into panels. This was also in our case. As you have seen during the first and the second lecture, they introduced mesh into the panels from pilot production. So we hit these samples with two balls. One is smaller and high, and one is bigger, to get 3 and 10 joule impact by steel balls. And the damage is noticed only after 10 joule impacts. It's nothing happened with 3 joule impacts. So it means that this material belongs to the category 2 because certain damage have been noticed after 10 joules. But it means that panels can be used for a zone when there is a limited size of impact. So if there is a heavy traffic, then it's better if it's category 1. The next parameter are related to chemical resistance of geopolymer products, and these parameters are very important because we have to take into account that geopolymers in chemistry, it's not the same as cement. So we cannot compare them directly or say that it fits for purposes before we test all these parameters. So the first one we have tested is carbonation, because this is important if steel reinforcement is incorporated in such material. Because if material is not resistant to carbonation, then there is a fall in pH value after carbonation process takes place, and this can accelerate corrosion. So we have exposed our samples for 56 days to 1% of CO2 and measure with indicators if there is any drop in pH value. There was no changes, so in our case, geopolymer panels are fully resistant to carbonation. Here you can see an example how it looks in concrete samples if they are not resistant to carbonation. The next parameter is alkali silica reactivity. This is also very important because such a reaction might take place under certain circumstances and cause expansion. And if it causes expansion, the material is deteriorated. So we also tested our geopolymer panels regarding alkali silica reactivities. Samples have been exposed to high humidity and elevated temperature of 38 degrees C for a whole year. So it has been confirmed that there is practically no expansion. In fact, samples shrank a bit and stayed stable over 12 months. So for the cement-based material, this limit is here, is 0.1%, but the alkali silica reactivity of our samples is far below these values. The next parameter, which is also related to the chemical reactivity or chemical stability of new developed product, is resistance to sulfate environment. So also exposure to sulfate environment in the case of cement can cause some expansion and later on deterioration. In our case, we have exposed our samples to sodium sulfite and tested them for 30 weeks. And again, as you can see here, no expansion was detected. And here are given the limits for cement-based material, because for geopolymer-based material, there is no limit set yet. So we need to stick to the cement-based and pay attention if something anyway happen in these systems. So in the case when such panels would be used in environment where we have simultaneous action of salts and freezing, it's also recommended to do freezing tests in the presence of de-icing salt. This is not required by ETICS-004, but since we know that this might be a problem, we introduced also this method from the RILEM Technical Committee. So in our case, we exposed samples to 3% sodium chloride solution, but samples did not withstand these conditions because chipping and scaling, what you can see here, of the material on the surface occurred. But I would say that this is good to know in advance to avoid using such panels in, for example, marine environment, so to prevent certain damages. So I have shown now results on results on samples developed in laboratory, but the same methodology was used also for the samples from pilot production. So I will not repeat the whole procedure now. I will rather summarize results for the sample from laboratory production as well from the pilot production here. When we have a look on these values for mechanophysical properties, we can conclude that there is very good correlation between pilot and lab production. Practically, values are pretty the same. For example, porosity, absorption, density are very similar for lab and pilot production. The density is a bit higher for pilot production, and consequently some other values differ a bit, like water vapor permeability and bond strength and water vapor resistance coefficient. But still we can have a conclusion that there is a very good agreement between laboratory panel production and pilot production. What we can also conclude here, that all the values are comparable to the cement-based products, and if this is a cement, it would fit for the intended use. Then additionally, also durability tests have confirmed that newly developed products are resistant to freezing, resistant to carbonation, resistant to alkali silica reaction, and also resistant to eventual sulfate attack. Products are not resistant if exposed to the freezing in the presence of de-icing salt, both on the laboratory and on the pilot production. What means, as I said before, that they have to be excluded from the use, their use excluded from the environment where salt and freezing act simultaneously. So, and again, also here is the evidence that the results of tests from laboratory and pilot production is in a very good agreement. So what we will also see from next two slides, where there are more detailed data graphically presented for alkali silica reactivity and for sulfate attack. We can see here the limit value set for the cement-based materials, and we can compare now results from the pilot production for 1 year and from the laboratory production for 1 year. For pilot, we have only 6 months because we received samples later, but still we can see that the results are very similar, so there is a good agreement with the laboratory and pilot production. And the same can be said for the resistance to sulfate attack. Values are far below the limits for the cement-based materials, and also here we can see the trend for the laboratory production and trend for the samples from pilot production are practically the same. So if I jump to the conclusions, I would say that we have established the methodology for testing of newly developed building products, so that panels fulfill all the requirements which are set for cement-based materials, that material exhibited excellent durability performance except for the resistance in the presence of de-icing salt, and that there is a very good correlation between results from laboratory and from pilot production. So, based on these test results, panels are suitable for intended use, except, as I said before, in areas where salt exposure could occur. And this is the first confirmation of fitness for use. Next steps are results from monitorings on site in different climate conditions, what will be present in the next section of our conference. And I can conclude that if both testing from laboratory, from pilot, and also from on-site, if all testing are positive, the future producer has certain guarantee that products are suitable for intended use. And after they set up pilot production line, they can apply for the European technical assessment, which is the document with which they will be able to come on the market. So this is from my side. Thank you for your attention.
Thank you, Wilma, for interesting presentation as well. So the testing of new materials is challenging. So I see that you manage this very well. So now is the time for the question answer session. We have 3 questions asked to some people. I'm going to read them. First is to Daniel. One of the challenges of the construction sector is different legislation of EU member states in terms of secondary raw materials implementation. What could be of your advices in respect? Daniel, as we are going a little bit out of the time, please give the feedback very, very shortly.
Yes, this is the problem, and I think that we should harmonize that. I think that European Union is working on that to get harmonized legislation. And also, I think one aspect here is standardization, to have to quickly follow the new technologies that will be developed. Usually, it takes a lot of time to shorten this time to get standards and harmonized legislation.
Okay, perfect. Thank you, Daniel. The next question is to Sergio Tamburini. How does the performance of your Geopolymer look if compared with other materials, traditional cement, in example? So little bit grammar, but Sergio, please, if you could say quickly the feedback.
Thanks for the question. The geopolymers used have important peculiarity compared to other binders. From the point of view of sustainability, intrinsically, as I've already explained, they are more environmental sustainable than organic resin, for example, cement, plasterboard, with less production of carbon dioxide. From a technical point of view, as Vilma, from ZAG, as in the last presentation, has explained exactly the limits and point of strength of a mixture we have used respect, for example, cement used in this project. But I can add an important motivation why we have chosen geopolymer for this project. This has the ability to accept a large quantity of construction demolition waste as inert material. We have inserted about 50% or more. On the other hand, cement has a problem in accepting construction demolition waste, in particular concrete, due to the fact that there is a residual activity that can change the characteristic of the final material produced. And this is a quite important peculiarity of geopolymer. Other important peculiarities
Sergio. Sorry for disturb you. So I think the key aspect has been mentioned. Moreover, I will write the email address on which each of the guests could ask us as a consortium about the aspect. Thank you. Now I want to pass to Maria Papa. The question is, you have mentioned that the pilot plant follows the Six Sigma methodology. I appreciate it. Are the key staff in your company certified for implementation of the methodology? I think, Maria, this is obvious and is enough if you confirm that.
Yes, exactly, Emil.
Exactly.
Regarding the production manager, yes, he's certified. The managing director is also certified by the European Project Management Association. Some key engineers, the mechanical and the electrical engineer that were involved in the pilot plant production, are certified by a university in North Greece in Thrax. And also the other personnel that was involved is trained according to this protocol of the Thrax University.
Okay, perfect. Thank you, Maria.